Welcome to the session on solution of linear ordinary differential equation of higher order with constant coefficient. In this session, we shall see about types of solution for linear differential equations of higher order. Usually, a linear differential equation will denote it as f of d into y is equal to g of x. Here y is a independent variable and x is independent variable, and this capital D indicates d by dx. There is something like derivative term with respect to x. Here f of d is a linear function in terms of capital D, that is in general can be written as a naught of x, or in simple we write it as a naught into d power n plus a1 into d power n minus 1 plus a2 into d power n minus 2 plus so on, plus a n minus 1 into d plus a n. This polynomial term in terms of capital D is known as the differential operator function. And here a is a function of x alone, there will not be any term of y, and d are nothing but d by dx. When I consider this LHS term, that is f of d into y, this term becomes something like d power n into y term we'll get in the first one. This is nothing but nth order derivative of y with respect to x. So that is dny by dx power n. Okay. So similarly we have the lower order derivative terms. So this function is called differential operator, and this is called a linear differential equation of higher order. Usually here n will be considered greater than or equal to 2. If it is 1, then it will be called linear differential equation of order 1. Higher order means order of this differential equation is greater than or equal to 1. For this type of differential equation, we can see two type of solution. I've directly taken here the equation. So for this type of differential equation, we can see two type of solution. One is called the complementary function, and we denote it as yc, and the other is particular integral, we denote this as yp. This complementary function yc is such that when I operate the differential operator f of d on yc, this will become 0. That is actually a vanishing part of the solution. Sum of these two solutions, we refer that as the general solution. We'll denote this as y. Okay. So in this complementary function, we will get arbitrary constant, and this complementary function number of arbitrary constant depends on the order of the differential equation. That can be written as c1 into y1 plus c2 into y2 plus so on plus cn into yn. The number of arbitrary constant is same as the order of the differential equation. Okay, and here y1, y2, yn, each one will be again a vanishing solution. That is, when I operate f of d on this function yi, it will become 0. And one more condition is these yi are linearly independent. That is, I cannot each of this yi is linearly independent. That is, I cannot make this combination, that is this, whatever I take this combination c1 plus c1y1 plus c2y2 plus so on plus cn yn, this linear combination at 0 unless I choose ci's, all ci's are 0. Okay? So such functions we call it as linearly independent. Okay, these yi's are linearly independent. Their combination is called the complementary function yc. In this session, we have seen what is complementary function. Next, we will see what is the particular integral. This is, you can see that this differential equation, the complementary function, we are not bothered about the RHS part. Whatever RHS part is there, we are just taking something like 0. So this RHS part will play effect in this complementary function. This will be non-vanishing part of the general solution. That is, when I operate f of d on this particular integral yp, I will get this is equal to g of x. Operate on yp, I will get this is equal to g of x. Okay, this yp is called the particular integral. So that's it about the complementary function and particular integral. Now coming to the linear differential equation, that is f of d into y is equal to g of x. This is classified into two types. One is called homogeneous, yes, and the second one is called non-homogeneous differential equation. In this homogeneous differential equation, we will have that function, actually we call this as force function, g of x is equal to 0. And in this non-homogeneous part, g of x not equal to 0. When we have a homogeneous differential equation, the general solution will contain only the complementary function, will not contain any particular integral. And when it is a non-homogeneous equation, we will get both complementary function and particular integral in the solution. Okay. That's it about the solution of differential equation.